All right, so let's talk about NMR a little bit more, maybe with another alkene type example. It's kind of a situation where the rules don't all obey that 3 bonds away type thing. So let's say we have an alkene like this. All right. So first thing we got to do is figure out how many different types of hydrogens there are. So the first thing I always do is I draw in all the hydrogens. It's the first thing I would do. There's an H. I'm gonna use my finger tonight. H here, an H here, and H here. So there's 3 as a CH3 there. So the next question then becomes labeling all the different ones. So how many different types of hydrogens does this molecule have? I would say 4, right? So I'll circle them. You can label them A, B, C, and D. Good. All right. So now the the general rule is 3 bonds away is where the hydrogens are essentially close enough to hear each other, right? Their little magnetic fields can interact. But now the problem is the other thing to think about here is, oh, look at that.
That's sweet.
Did that go away? Hold on a second. All right, a little detour there, a new feature. Notice the giant arrows that are pointing towards nothing. Right? So normally we say 3 bonds away is kind of the key spot. Reasons why that is different is usually if things are locked in conformation, right? They can't freely rotate. Right? Free rotation, right, will affect what you can hear or not. So when there's a pi bond, right, we all know you can't rotate about a pi bond, otherwise you break the pi bond. So in this case, let's look at A first of all here. So A, right, if we just drew it, so here's A. Let's say here's A, we're going to draw its splitting tree. Everybody starts out as a singlet, right? So I would say A can for sure hear B. So B is going to split A into a doublet, right? That's the J from A. That's the splitting from A to B. Alright, so it splits into a doublet. So now it's a doublet. Alright? So that checks that off. What else could A probably hear? Probably could hear C too, right? Because they're cis to each other about that alkene on the same side. So A, even though, right, so this is one of those things you get used to, that just because hydrogen's on the same carbon, right? A and B are on the same carbon, but they're not the same hydrogen. So just because you're on the same carbon doesn't mean you're the same type of hydrogen. Right? So A is cis to C, right? And how is C going to split A? If C is near its neighbor, and there's one hydrogen, C hydrogen, so it's 1 plus 1, A will be split into 2 into a doublet by C. But A was already split into a doublet by B, so we just keep on splitting. Right, so now we have something like a doublet of doublets, right? Because this is the A to C split. So in reality, we could have a peak that looks like this. That's worth 1H by its integration, right? And it's going to be pretty D-shielded, right? Because it's perpendicular to the pi bond. Right, this is going to be perpendicular pi bond, so it's going to be pretty D-shielded. A, B, and C are all going to be around 5 or 6 because of that. All right, let's look at some E2 stuff, essentially. It would be E2. We of course know E2 means anti-periplanar elimination, one-step planar anti. Right. One step, concerted mechanism, strong base. Right, so I'm just going to make the base right away. Say it's O minus. We'll make it big. because it's E2, we don't want to do SN2s. And the question was, to take it even a step further than before, what if we had to do it in a cyclohexane ring? So let's see if we can still do our chair conformations. So let's bust out our wedges and hatches. So let's see, we'll put BR over here. The CH3 wedged and an H coming out S. Good. So we need to get an anti-periplanar. That means we need to get the H and the BR on opposite faces. So what we also need to be able to do is take this cyclohexane ring, right, and convert it into a chair structure. Right. So can we do that? So let's first just work on drawn chairs. 2 plain and thin, 2 more, there and there. Right. Can we draw chair structures? That's the first thing. 2 parallel lines. Right, 2 parallel lines. 2 more parallel lines, and yet 2 more parallel lines. Connect them all together. Yep. Going up, axial, equatorial. Axial, equatorial. Right? One thing people always forget, so if you're axial, does that mean you're always up? No, it's every other carbon, right? So this ring, right, has a top and a bottom. The bromine and the H, let's say, are on the top. They're pointing up. The CH3 is pointing down. It doesn't matter which carbon I pick, right, to be whatever when I want it to be. Let's just label them. Let's make this 1 and this 2, and this will translate to this being 1 and this being 2. And I did that on purpose to make my life easier, right? Oh, I screwed this up.
You have an extra arm.
No, I just screwed it up. It's impossible to do an elimination this way, but we'll do it. So it's good to look at, right? Let's say we put the bromine on the top because it's pointing up. The H is also on the top face, so the H is on carbon 2, so is the H going to be axial or equatorial? Has to be equatorial, right? Everybody see how this H is pointed up and this bromine's up, and they have to both be in the same face here? Right, they have to be. So that means this axial position has a CH3. Good.
So you want up axial.
But now, so there's probably an H right here too. The problem is this: can I do? Is there any way in this ring I can make this bromine and this H ever be anti to each other?
We're going carbon 6.
Well, you have to
On this carbon, I'd have to break. This H and this bromine are forever cis to each other. I screwed that up, right?
This was to be hatches on the bromine.
Nah, it doesn't matter, right? You can see this.
The hydrogen has to be on the.
So,
equatorial.
We'd have to. The hydrogen has to be axial.
Bromine would have to be on the up.
I would have to flip it around. So let's look at carbon 6. Would also have a, right? It would have a H axial and another H equatorial. So now maybe you can see this H to this bromine, right? This H to this bromine. There's that anti-periplanar relationship we needed, right?
Did you just draw an H on carbon 5 and carbon 6?
So carbon 6, let me label carbon 6. This is carbon 6 from there. So carbon 6, carbon 5, carbon 4, and carbon 3 all have 2 H's on it. They're just not drawn in there.
I was just saying, because you put an H going down there too.
On carbon 5?
Yeah.
Nope, so on carbon 5, the H is going to be going up, axial,
Or it says carbon 3.
down, equatorial. Right, carbon 3 is going to have, let's see, down H on carbon 4, axial, up H. It's going to have an up H and a down H. Right, you can get a little hairy.
Oh,
there.
I
That's-
see how.
see how it is?
Okay.
I mean, this is pretty tough. But you're gonna see. I can tell you right now that some of the papers I'm gonna have you guys read. You're gonna be in chair confirmations. You're gonna be figuring out transition states, right? Things things in organic chemistry like to get in 6-membered rings, right? It's a lower energy transition state. Even if it's the height of that hill, they want to get in these little ring systems, right? Makes them more stable.
So equatorial up and equatorial down are also anti-perioplanar.
Yes, they are. But it's harder to. Are they? They're not quite. You have to be axial to get anti-periplanar
Alright.
fully. Yeah, you're not quite there yet. You have to be in the axial position to do this elimination. You can't do it from the axial. So let's look at our resonance structure one. Let's say we take pyridine that has been protonated. And let's say the OH is either here, para, or the OH could be meta. Which one of these is going to be the stronger acid? So the question is, which is the stronger acid? More to the point, that's more reactive acid, right? Reactive acid. That's basically asking, which one of these has the more reactive NH bond? Which one of these has a more reactive NH bond? So if I want to make this bond reactive, do I want to push electrons towards it or pull electrons away from it? To make this bond weaker, to make it more reactive, do I want to push electrons towards it or electrons away from it? If I want to make this more delta plus, I want to make the H more delta plus, so I want to put electrons towards it or away from it? Take them away. Okay, so which structure is going to do the best at taking away or at least not giving them to it? So we've decided this was the one that's going to be more acidic, that this bond is going to be weaker, more reactive. So I'll draw a resonance structure for this one where electrons can go here. Oops. They come down from the oxygen. Pi bond moves over. Electrons go to the nitrogen. Right. So I'm doing a couple steps there at once.
Yeah.
Obviously, you could draw intermediates here, but I just want to do this to prove a point right away. Of course, when we draw resonance structures, we always want to balance our charges. So it looks like this resonance structure actually relieved the nitrogen of the plus charge, right? The nitrogen here was relieved of this plus charge. When the nitrogen has a plus charge in NH, that's a much more reactive NH bond. So now we've actually made this NH bond less reactive, right? Because we've found a way to get the nitrogen to not have that plus charge. With this one, we can't do that. There is no resonance structure where we can move electrons such that, the nitrogen, right, cannot have that plus charge. You can put next to it, but you can't get it right there. Right? So this is going to be the less acidic. This is a little bit of a stronger bond, less reactive. So
You can't have two pi bonds.
you can't have two pi bonds next to each other, right? So this is a good practice just to see. So the other one, if I drew electrons here, right? If you make a bond, you got to break a bond, right? You can't, right? Carbon can't have more than 4 bonds. So then those electrons would go right to that carbon, right? Electrons are now on this carbon as that new pi bond was formed. Post charge. Remember, overall charge was +1. So we're still good there, right? But you notice, right, this negative charge, it's close, right? It's close to this positive nitrogen, but it never gets to the point where it totally helps get rid of the nitrogen with the plus charge. So this is still a more reactive
Nitrogen always
NH.
has a plus charge.
And there's no way I cannot have nitrogen have a plus charge. I mean, there is, but
We haven't got the
no, there is, but it's not that great. Right?
Because you can move those electrons over to nitrogen, but then you have to move the other bonds all the way up and take oxygen back down.
Right.
So
right? Everybody has full octets here. Everybody has full octets here, but you got a lot more charges going on, right? Also just not great. Just looking at it, you'd say there's up 2 pluses and a minus, versus just a plus. You say it, as far as stability goes, obviously you can see this is more reactive, more acidic. Okay, let's talk about tautomerization. A couple examples I would use just to start. So let's look at acetone. Acetone can tautomerize, and honestly, I did draw that mechanism up, and I kind of highly regret it, because really it's probably a step. It's more than one. Can't happen all at once, right? But the gist of it is, the H that's alpha, one of the alpha H's, ends up on this oxygen and you form a new pi bond.
How does that happen?
Well, I mean, well, it has to happen. Wait, okay, well,
So basically,
how does it happen? What needs to happen what new bonds need to form, what old bonds need to break, right? So what bonds need to break?
a CH bond.
Not the double bond,
pi bond on the OC.
the CO pi bond, right? This is just a pi bond, right?
Yeah.
And
CH.
the CH sigma bond, right? And we need to form
CC pi bond.
CC pi bond,
And an OH sigma.
right? So we need to figure a mechanism that does that. Now the one I showed you guys, it did all at once. Probably not fair. It probably is stepwise, where this, I would say this H would probably just leave. You'd get a charge separation, like an enolate. And that gets you to your tautomer, right? The H falls off, make an O minus, the O minus grabs the H, right? You get the tautomer. The enol, right? The enol.
It always falls off, right? The H always falls off?
Yeah. That bond has to break.
Yeah.
Some way, shape, or form. It could be, right, you can think of 2 molecules of acetone coming together to do this for each other, maybe in a 6-member ring transition state. Perhaps.
Do two hydrogens tautomerize at the same time? Is that possible?
Oh.
No,
No?
just one at a time. Right? So
Could one go and another one go?
no, because
You
how
get a
many
bigger molecule.
bonds does carbon want to have? You can't. I
You
can't.
get a bigger molecule.
I can't keep tautomerizing.
Yeah, I know. I'm saying get a bigger molecule. Could it happen on the same molecule?
Yeah. If there's different ketones or different carbonyls. Yeah, you could do more than one tautomerization. So, right, acetone exists in a bottle, so it doesn't exist like this enols, right? So this equilibrium lies very far to the left, right? So can you guys think of an example where I could get it to be more in the tautomer form? What could I do? The question really then is, how can I make this CH bond weaker, more reactive? What could I do to make that bond more reactive? I could add solvent, right? Absolutely, solvent could make a difference. Not solvent, like structurally. What else could I add to the molecule?
You
Electron
activate
withdrawing
the
group.
activate the carbon and acid of some sort? Does that
No,
work?
no, I'm not. So yep, you can make this equilibrium shift by adding a catalyst, right? Adding H plus. But I'm saying just what could you add to the molecule?
An electron withdrawing group.
You could put an electron
Over there.
put an electron withdrawing group here, right? That would make this bond that much more reactive, right? More polar, right?
So if you added like an OH group there or something?
I wouldn't do an OH, right? Because OH is right. OH is pretty, but you could do
Nitrogen?
a what?
Like a nitrogen?
What are you going forwards or backwards in electronegativity? Nitrogen's more or less than oxygen.
Okay, so you can do like
Throw a fluorine on there, right? One of the things you'll see an example of a lot of times, we talked a lot about this, was what about if you have a dicarbonyl, right? Right, because of resonance, right? This tautomer, they can go either way. Bless you. Right, now this tautomer, right, you can go either way, right? So these are pretty reactive CH bonds, acidic ones, right? Reactive ones. They're easily tautomerized, they're easily deprotonated with a strong base to make an enolate, right? A stabilized enolate.
So it's a more balanced equilibrium then?
Yeah, so this equilibrium, right, there is, I mean, it's not, this is like 0.01, 0.1% maybe? This is, I don't know, maybe this is more than 0.1% before I get all ahead of myself, right? But it's certainly more, right, because this is a weaker bond, right? It's more stable like this, right? There's a lot of things going for it, right? It's alpha, beta unsaturated. You notice how now it's conjugated, right? There's all sorts of little things going for it there. Yeah.
Could that second hydrogen make another double bond between that carbon? The carbon two double bonds going opposite ways?
It cannot, because if I break this, if there's a CH here, right, to do that elimination, I need to be lined up with pi star, and I can't get lined up with pi star from this angle.
Could it do it from the other side? Is that what you mean?
So
There's
it's
only
not
one-
re- it's
nope.
not reactive.
I mean, on the other side, like the other carbon.
This one?
Yeah.
Yeah, this one could, this one could tautomerize though.
That's what it was.
Yeah, this side could tautomerize. This one can't. But this guy, you could
Would always pull from
Yeah,
the
no.
middle first.
pull from the middle first, right? Because this is going to be the one that's, right, the most, right, this is the weakest, right? Because it's between the two carbonyls.
Yeah, but
And
that-
forms a really stable product.
That other hydrogen can.
Over here could too, yeah.
Yeah, but you could form that double bond on that other side and then do the same thing with the CH3 on the left side, right?
This side?
Move that up.
You could do it here and then do the, yeah.
Yeah.
It doesn't these yeah, they're the same. I could have just as easily done the double bond on this side too.
Okay.
Absolutely. So,
Sweet.
so now let's look at this one though. Ready for the kicker? Draw me the tautomer of this. So if we're looking at this, right, throws you off a little bit because you're so used to the alpha CH, but now we just have to go to the alpha beta gamma CH, right? If that one of these CHs, right, tautomerizes and ends up over there, what's our product going to look like? It looks like phenol, right?
So the
And
other
that why would it?
Those electrons.
Yeah, so it's going to really lie over here, right? Because, right, this product, this tautomer is what? It's aromatic.
The other pi bond just moves when you form the first.
Right, so you could think about it, I mean, here's the quick and dirty way to do it, right?
Go and grab the H.
You could think about actually the pi bond grabbing the H.
Sure.
Oh,
These electrons going there.
And then that pi bond will get over.
can you do it a different way? Can the H
You could do it stepwise, like I did up here.
Away,
so
Just have the H go away,
and then come back.
right,
And then you go down.
and have
so you
the,
could have an O minus and then that minus takes.
Yep. absolutely. It's a good one. That's right from the book, Grossman, chapter 1.